So this is just a short story. So let's just look at a few other examples. If you looked at the El Nino teleconnections and La Nina teleconnections, Indonesia and parts of Australia are very heavily affected. So, for example, La Nina doesn't have so much of an impact here, but El Nino does in December, January, February. El Nino also has lots of winter effects in the southern hemisphere, but slightly different over the winter and so on. So that is exploited, and the weather forecast, S2S forecast in Australia is quite advanced, especially in terms of translating those forecasts into useful information for farmers for managing crops, irrigation, and so on. So this is showing the ROC area of probability of the occurrence of heat wave, so extreme heat extreme heat factor index greater than 0. For a definition of the index, we have to look in the book. For all forecasts initialized in the months of December, January, February, their summer month, the verification at various lead times is shown: week 2, days 8 to 14, week 3, fortnight, and fortnight 1.5, and fortnight 2, and a month. So various levels of S2S timescales: week 2, week 3, weeks 1 and 2, weeks 2 and weeks 3 and 4, and a month. And you can see that based on the verification, where the reddish colors are, magenta, yellowish, and so on, out to these, everything is positive here. Only skills that are useful are shown. So you can see that there is lots of skill in the different regions at different time scales, and of course these are dependent on El Nino phases. So El Nino and La Nina enhance the skill quite a bit on Australia, which is what we talked about before. In terms of depicting the forecast, there are lots of details. I skipped the calibration of forecasts, validation, recalibration, and all those things, because I wanted to just give you brief flavor of the S2S in this course. But looking here at an example, probability of detection POD, false alarm ratio, where the model is predicting an event in a wrong way. Equitable threat score is another skill score of the dry spells, defined as standard precipitation index SPI, minus 10D lower than -1, calculated with moving windows of lead time. So don't worry about the details, but essentially the way this works is you want to be able to look at the probability of detection, false alarm ratios, and equitable threat score to say where the confidence is in the forecast. So it's not just showing this map and saying you have reliable skill, but it's also to provide further detail in terms of the probability of the usefulness of the information. Okay, this is the ECMWF forecast compared to EOBS data sets over the European region from 1995 to 2015. Different line of each score represents the scores by using various methods to extract dichotomous forecasts from the ensemble. So ECMWF still uses ensemble forecasts, and this is showing here equitable threat score for SPI less than -2. So various levels of drought, dryness or wetness are used to predict extreme wet and extreme dry periods, days, and these are the various lead times here. Okay, so just read up and make sure you understand that the forecasting business, how to depict the information, is not always just showing skill score. That's not what people use. Talking about cyclones, other mesoscale variabilities that are also predicted. This is a diagram from one of the book chapters by Chidong Zhang, which shows different phases of the MJO convection center. So in A, it's over the Indian Ocean, B, or the maritime continent, C, or the West Pacific, and here, or the Americas and Africa. So over here. And you can see that the cyclogenesis itself and the TC tracks vary depending on the phase of the MJO, and which is indicated by the location of the convection or the active phase of MJO. And that's understandable because cyclogenesis basically depends on vorticity. The seeds of cyclone are set by these convective activities and the waves, like the easterly waves and the Kelvin waves and so on. And the vorticity, mid-tropospheric humidity, vertical shear, vertical motion in the atmosphere and so on favor the growth of these cyclone genesis or seeds of cyclones into cyclones. Okay, it's not always easy to say which one will grow, but once they have grown into tropical depression, one can track other things in the ocean, like the so-called hurricane potential, which is the warm water available above 26-degree isotherm in the ocean and so on, which is what feeds the energy to the cyclone to grow. But nonetheless, the cyclogenesis itself is governed by the phase of the MJO, and large-scale low-frequency variability like El Nino. El Nino has a global reach, and it lasts for 9 to 12, sometimes 18 or even 24 months. So it's a very low-frequency process. So when you have typical El Nino, this is the typical El Nino influence. You have warm, wet conditions over here because the convection from the west has sloshed towards the east. So you get more hurricanes due to less vertical shear. So vertical shear tends to remove the energy from the cyclones and hurricanes and prevent them from growing. So you get, on this side you get more hurricanes due to less vertical shear. On this side you get fewer hurricanes due to stronger vertical shear and trade winds and greater atmospheric stability. Okay, you need unstable and vertical motions for moisture loading and favoring cyclone growths. Whereas during a La Nina, you switch the things around, so you have cool, dry conditions on here, strong upwelling. Galapagos is always cold, for example. Fewer hurricanes due to stronger vertical shear on the Pacific side, where we call them cyclones and typhoons. More hurricanes on the Atlantic side due to weaker vertical wind shear and trade winds and less atmospheric stability. For example, 2020 has just been declared the record, tying 2005 as the most numbered storms, and there were a large number of landfalls, and now also the cyclones are rapidly intensifying because of the moisture increase in the atmosphere, ocean warming. They are also moving slowly. They are stalling and dumping more rain on when they hit coasts and so on and so forth. Okay. Here is an example that just ended. Taukte hit the Indian region, started around May 13. This is showing May 16th. The track was along here, so the model did pretty well, and these were the forecasts, which were also really reliable. But nonetheless, the rapid intensification, which typically takes 4 to 5 days, happened in just 2 days here, and the cyclone seemed to almost stall when it hit land, and then it remained very strong even as it was on land, because it was interacting with the background monsoonal circulation and maybe some impact from the warm air on this side and so on. But even the cyclogenesis forecast has been advanced now. So this is week 1, 21 May to 27 May, and a cyclogenesis is forecasted to be very high. A cyclone is growing in the next few days. But for week 2 right now, the forecast says, so this is actual forecast, 28th May to 3rd of June. So I'm recording this on 20th of May. Okay, so both are forecasts. So even cyclogenesis, birth of a cyclone, is being predicted well in advance, which was also done for Taukte. So the models are really getting good at these mesoscale forecasts. There are regions in Europe and especially US where the so-called atmospheric rivers have large scales and long time scales which bring snowstorms and rainfall over parts of western US. So you can see that this is a 7-day lead 1000-kilometer threshold. This is a 7-day lead 500-kilometer threshold, and these are the 1996 to 2013 ECMWF ensemble atmospheric river hits versus forecast lead. Again, because of this persistence of the feature of atmospheric rivers, those are literally atmospheric rivers carrying as much water as rivers do in the atmosphere, bringing rainfall. So they have several days of lead time forecast, which is dependent on season. It is showing here November, December, January, February, March, as well as the other 6 months from May to September. Okay, so these are for the North Pacific and Western US, North Atlantic and the UK, South Pacific and Australia, South Pacific and Chile. Okay, so this is where the extreme weather event forecast skill is coming from. This is the 2-week occurrence forecast skill again of the atmospheric rivers. Again, multi-week forecast skill depending on the different seasons compared to reference climatology. So obviously there is significant and impressive skill in predicting extreme weather at various time scales and various features. This is an example of tornadoes, for example. Scatter plot of the number of US tornadoes reported in June on this axis, and the CFSV2 reforecast and operational forecast. You remember what reforecast is for the environmental tornado environmental index, and the correlation between the observed and the forecast reforecast here is 0.58, which is really good skill, because when we have to also consider the skill in terms of the regret and no regret decisions. For things like tornado, warnings can lead to a drill of taking shelter, which is a no regret decision, because if there is no tornado, there is no loss. Okay, but for other things like closing schools or shutting down beaches, transportation, etc., obviously one has to have much more skillful forecasts. Finally, this is a forecast skill of surface winter weather conditions. Correlation score for the frequency of winter storms measured by the 10th percentile daily sea level pressure minima. Observed storminess from ERA interim reanalysis is used here, correlated with forecasted storminess. Hatching indicates values above 90% statistical significance according to the student t-test, allowing for correlation. So there are regions where the skill is negative, but there are large regions where the skill is significant at 95% confidence, 90% confidence level compared to reanalysis. So again, winter storminess, remember this is often related to the polar jet stream and the polar vortex, so the stratospheric vortex and the tropospheric vortex or the jet stream. And you can see the large scale patterns often when you look at the skill as well. So high skill, low skill, high skill, low skill. So you can imagine that some phases of the winter storms are better predicted than others. Okay, so this is a short introduction to the applications of S2S forecasts. There are many good examples, and the number of examples will keep increasing because the S2S forecast run by Andy Robertson and Frédéric Vittard under the WMO S2S project is recruiting many groups across the world who are doing S2S forecast applications. Okay, so look out for more and more examples, and look for details on how specific sectors are served in terms of how the forecasts are portrayed, what kind of probabilistic information is provided, and what level of skill is required. The reinsurance industry may work with a very different skill level than a farmer, for example, or a water manager, or a ski ski site operation, and so on and so forth.